Okay, today we're going to learn how to graph y equals f of 1 on x when we've already been given the graph y equals f of x. Okay, and the example we're going to use to start off with is y equals log of x. Given y equals log of x, graph y equals log of 1 on x, which maybe you've never seen before. Okay, there are a few different ways you could graph this. You could use calculus, you could use limits to try and find the shape. Maybe you could draw y equals 1 on x first and then apply the logarithm to that to try and find the shape. But the way we're going to do it today is a method which basically says, given any graph here, if you let x map to 1 on x, so if you replace x by 1 on x, how do you obtain this new graph? So this method will work for any starting graph here. Okay. The first step is we want to draw the graph of y equals log of x because we want to be looking at this to use it to get the new graph. Okay, so there's y equals log of x, there's 1, and I'm just going to put a line through here because we're going to be looking at the regions between 1 and infinity and between 1 and 0. Okay, it's just a coincidence that there's a 0 here on this graph. We would still look at the regions between 1 and 0 and 1 and infinity, even if there wasn't a 0 here. Even if we had a different graph, like an exponential function, for example, we would still divide it up into the regions 0, 1, and 1 and infinity. Okay? So now that we've got that graph there, and you know, this graph could just be given to you, right? You might not even know what the function is, but in this case, it's log of x. So the question is, given this graph, how do we graph this thing? Okay? And what I'm going to do is I'm going to divide it up into the regions like we have over there between 0 and 1 and infinity. And then I'm going to look at these two separate regions. Okay, I want to look at what happens when x is between 1 and 0, for example. But when I look at the function, I've got 1 on x involved. So as well as looking at what x is doing, I want to know what 1 on x is doing. So I'm going to quickly draw up a table of values with x on the top and 1 on x on the bottom. So then when I want to look at what x is doing from, let's say in this region, from 1 to 0, when x is going from 1 to 0, what is 1 on x doing? Well, when x is at 1, 1 on 1 is 1. So 1 on x is also at 1. And as x is getting smaller and smaller, getting to 0, we're saying 1 divided by smaller and smaller numbers means that this quantity is getting bigger and bigger, eventually going to infinity in the limit. Okay, so what does that mean? It means when I want to graph this function, I say what happens between x is equal to 1 all the way along to x is equal to 0. But when I go to graph it, I say log of not those x values from 1 to 0, but the reciprocal of those x values from 1 to 0. The reciprocal of those values from 1 to 0 are basically values from 1 to infinity. So I want to take the logarithm of values going from 1 to infinity. So I come back to our log graph, and I want to take the logarithm of values going from 1 all the way out to infinity. So what does that mean? It means that what happens on this graph between 1 and 0 is what happens on this graph between 1 and infinity. So the stuff that happens on this graph between 1 and infinity is compressed or shrunk, if you like, to fit into this graph between 1 and 0. Okay, and so now we can graph it, because what happens is it goes from the axis up to infinity as we go this way. So we'll go from the axis up to infinity on this graph. Okay, and there's the first section. Okay, and now we need to do the second section. So the second section will be this bit over here, when x is going from 1 to infinity. When x is going from 1 to infinity, we ask what is 1 on x doing? Well, 1 on 1 is 1 again. And we're saying 1 divided by bigger and bigger numbers means that this is eventually getting smaller and smaller and eventually getting to 0. Okay, so when we want to take the log of values from 1 all the way up to the log of infinity, sorry, that's not correct. When we want to look at what this function is doing at values from 1 to infinity, we need to take the logarithm of the reciprocals of those values. So we're not taking log of 1 to log of infinity, we're taking log of 1 to log of 0. So we come back to our log function, we're taking log of 1 to log of 0. Okay, and now you can see what happens, because when we look at this graph, we see that from 1 to 0, the graph comes out of the axis and goes to negative infinity. It comes out of the axis and goes to negative infinity. And there you have it. There's the graph of y equals log of 1 on x. It should just be a smooth decreasing function going down like that. Okay, so just to sum up, the way we graphed this, given this graph, was we looked at what happened from 1 to 0, and we stretched that out to happen between 1 and infinity. And we looked at what happens between 1 and infinity, and we compressed that to happen between 1 and 0. Okay, so now we'll just move right along and give you another example to practice this. Imagine if you had a sine function and you wanted to graph y equals sine of 1 on x based on what the graph of y equals sine of x looks like. Well, the first thing that we need to do is we need to sketch y equals sine of x. Okay, so y equals sine of x looks like this and keeps going, and looks like this and keeps going. And we need to put in the values of 1, and now we have negative values, so we need to put in -1 as well. So 1 occurs, this value here, which corresponds to the peak, is pi on 2, and pi on 2 is about 1.5. So 1 is going to occur just to the left of it, down there. So that's the point which gives us 1, 0, and infinity. And now the same thing over here. The x value, which gives us the minimum here, is about -1.5. So 1 is going to be just to the side of that, down there. So that's -1, and I haven't really drawn this to scale. That should be 1, and that should be 1, and they're different sizes, but that doesn't matter. And there's minus infinity. So we want to look at the region 0 to 1, 1 to infinity, 0 to -1, -1 to minus infinity. Okay, so we're all set up nicely there. And we want to do the same thing as we did before. We want to look at those regions there and there, from minus infinity to -1 to 0 to 1 to infinity. And you could draw a table like this again, but really you can start just doing it in your head, right? You look at the graph and you say, for example, what happens between 1 and infinity? Well, what happens between 1 and infinity is what occurs on the original graph between 1 and 0. So you just do the opposite, right? 1 to infinity means you go 1 to 0. Okay, and looking at that graph, what happens? It goes from, it's not quite at its maximum, which is 1, so it goes from just below 1 down to 0. So it goes from, if that's 1, it goes from just below 1 down to 0. Okay, and looking at the negative part of the graph, so if that's a -1, looking at the negative part of the graph, what happens out here? I'm not going to draw it, I'm just going to quickly talk you through it. From -1 to minus infinity, well, you look at the opposite region. So you look at -1 to 0, and you see that it goes from just above the minimum, so just above -1 to 0. So just above -1 to 0. Okay? Now we want to sketch this region in here when x is going from 1 to 0, and then when x is going from -1 to 0. So when x goes from 1 to 0, you look at the opposite region, 1 to infinity, and you say, what's happening? And you see that the graph is basically increasing up towards its maximum and then oscillating an infinite number of times. So if we want to draw that, we have to increase up to the maximum, and then we need to oscillate an infinite number of times. I'm going to have trouble drawing this, so you can see that it's going back and forth and not really, it's not being a sine curve anymore, but I can't draw it. So that's the idea. And the same thing happens on this side. It increases to -1 and then oscillates an infinite number of times. So there you have it, a very unfamiliar looking graph. Okay, and of course you can check what this looks like using something like Wolfram Alpha to maybe get a better picture than my drawing. Okay, and we'll finish there, but I'll just quickly give you 3 more examples that you can practice with. Imagine if you had y equals x. Could you use that to graph y equals 1 on x using the principles that I've just described? Imagine if you had y equals e to the x. Could you use that to sketch y equals e to the 1 on x using the principles I've just described? And lastly, imagine if you had y equals inverse sine of x. Could you use that to sketch y equals inverse sine of 1 on x? And of course you can check all your answers to those. Well, you probably already know what this one looks like, but you can check your answers to these using a website like Wolfram Alpha.